Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish, just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the universe's deepest mysteries, dark matter, the invisible substance that holds everything together. We'll discover that most of the universe's matter is completely invisible, that galaxies would fly apart without it, and that this cosmic glue shapes the structure of everything we see despite remaining utterly hidden. The answer to what holds the universe together isn't what we can see, but what we cannot. But don't worry, this isn't going to be an overwhelming journey through impenetrable physics or a dizzying plunge into abstract mathematics. Instead, we'll move slowly and thoughtfully through the evidence, building understanding piece by piece, finding clarity in this invisible architecture. By the end, I think you'll have a richer appreciation not just for what dark matter is, but for how profoundly it shapes reality itself. If you enjoy these calm explorations of cosmic mysteries and invisible structures, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand, and release it gently. Feel yourself sinking deeper into comfort with each exhale. And let's begin our slow drift through the invisible universe, exploring what holds galaxies together, what shapes cosmic structure, what comprises most of reality, yet remains completely hidden. There's nowhere you need to be, no boundaries you must cross. Just listen, and let the mysteries of the invisible unfold like dark matter itself, permeating everything yet touching nothing. The story of dark matter begins not with what we saw, but with what refused to make sense, with observations that violated our understanding of how gravity should work. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a vast collection of over 1,000 galaxies bound together by gravity. He measured how fast individual galaxies were moving within the cluster. Their velocities were surprisingly high, far faster than expected. Using Newton's laws of gravity in the visible mass of galaxies, Zwicky calculated how much mass was needed to hold the cluster together gravitationally. The galaxies were moving so fast they should escape the cluster's gravitational pull, yet clearly they remained bound, orbiting within the cluster. Zwicky concluded there must be far more mass present than what was visible. He called this unseen mass dark matter. His calculation suggested the Coma Cluster contained about 400 times more dark matter than visible matter. This seemed preposterous. Most astronomers dismissed Zwicky's conclusion. Perhaps his measurements were wrong. Perhaps he misunderstood the cluster's dynamics. But Zwicky was right, though it would take decades before the astronomical community accepted this revolutionary idea. The problem was simple yet profound. Visible matter, everything we can see through telescopes, wasn't enough to explain observed gravitational effects. Galaxies moved too fast. Clusters held together too strongly. Something invisible was providing additional gravity. This invisible mass didn't emit light at any wavelength. It didn't absorb light either. It was completely dark, detectable only through its gravitational influence. The discovery represented a crisis for astrophysics. If most of the universe's mass was invisible, our understanding of cosmic structure was fundamentally incomplete. For decades, Zwicky's dark matter remained a curiosity, an anomaly few took seriously. The idea seemed too strange, too contrary to observation. After all, astronomy is fundamentally about seeing. We understand the cosmos through light. How could most of it be invisible? but evidence accumulated. In the 1970s, Vera Rubin studied how stars orbit within galaxies, particularly in spiral galaxies like our Milky Way. According to Newton's laws, stars farther from a galaxy's centre should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. The mass is concentrated at the centre, so gravitational pull weakens with distance. Orbital velocity should decrease with distance from the galactic core. But Rubin's careful measurements showed something completely different. Stars far from galactic centres orbited just as fast as stars closer in. The rotation curves, graphs of orbital velocity versus distance from centre, remained flat rather than declining as expected. This violated basic physics unless there was more mass than visible. Much more mass, extending far beyond the visible galaxy. Rubin had discovered that galaxies are embedded in enormous halos of invisible matter, extending perhaps 10 times farther than the visible stars. This dark matter halo provides the gravitational glue holding galaxies together and keeping their outer stars moving at observed speeds. Without dark matter, galaxies would fly apart. Their rotation is too fast for visible matter alone to maintain gravitational binding. The dark matter halo acts like invisible scaffolding, a gravitational framework supporting and shaping the visible galaxy. Rubin's work, more systematic and careful than earlier studies, convinced the astronomical community. Dark matter was real, not a measurement error or misunderstanding. By the 1980s, dark matter was accepted as genuine phenomenon requiring explanation. But what was it? It couldn't be ordinary matter that simply wasn't glowing. There wasn't enough of that to account for the missing mass. It had to be something exotic, some new form of matter unknown to particle physics at that time. The discovery of dark matter's prevalence marked a revolution in cosmology. The visible universe, everything we'd studied for centuries, was just a tiny fraction of total matter. We live in a cosmos dominated by the invisible. Stars, planets, gas, dust, everything made of normal atoms comprises only about 15% of matter. The remaining 85% is dark matter, invisible and mysterious, known only through its gravitational effects. This invisible majority shapes cosmic structure. It forms the skeleton upon which visible matter accumulates. Galaxies form where dark matter is densest. The cosmic web of filaments and voids traces dark matter's distribution. Understanding the universe requires understanding dark matter. We cannot comprehend cosmic structure without accounting for the invisible scaffold. The discovery of missing mass transformed astronomy from a science of the visible to a science acknowledging that most of reality is hidden. This epistemic humility, recognizing that we see only a small fraction of what exists, is crucial for modern cosmology. Dark matter reminds us that direct observation is limited. Much of reality remains invisible, knowable only through indirect effects. If dark matter is invisible, how do we know it's there? The answer lies in gravity, the one force that dark matter cannot hide from. Gravity is universal. Everything with mass generates gravitational pull. Even invisible matter curves space-time and attracts other matter. Dark matter doesn't emit, absorb, or reflect light. It doesn't interact electromagnetically, but it has mass, so it generates gravity. This gravitational signature is how we detect dark matter. We observe its effects on visible matter and infer the invisible cause. Rotation curves provide one detection method. By measuring how fast stars orbit in galaxies, we infer how much mass is present. If visible matter alone existed, outer stars would orbit slowly, but they orbit quickly, requiring additional invisible mass. The rotation curve reveals dark matter's distribution. Flat curves indicate extensive dark matter halos surrounding galaxies. Gravitational lensing provides another powerful detection method. Einstein's general relativity predicts that mass bends spacetime. Galaxy cluster dynamics provide additional evidence. Clusters contain hundreds or thousands of galaxies plus hot gas. The gas temperature reveals how deep the gravitational potential well is. Hotter gas requires deeper potential, meaning more mass. Observations consistently show that visible matter, even including hot gas, is insufficient. Dark matter dominates cluster mass. Cosmic microwave background observations constrain dark matter's properties. The CMB shows imprint of density fluctuations from early universe. These fluctuations grew into cosmic structure. Their growth rate depends on total matter density, including dark matter. CMB measurements determine that matter comprises about 30% of universe's energy density, but visible matter is only about 5%. The difference, about 25%, is dark matter. CMB observations require dark matter's existence for consistency. Large-scale structure observations show the cosmic web, filaments of galaxies separated by vast voids. Computer simulations starting with dark matter produce structures matching observations. Without dark matter, simulations fail to reproduce observed patterns. Dark matter provides gravitational seeds around which visible matter accumulates. Structure formation requires dark matter's early gravitational influence. All these detection methods converge on consistent conclusion. Dark matter exists, comprises most of universe's matter, and shapes cosmic structure. The evidence is overwhelming. Multiple independent observations from different astronomical systems all require dark matter. This convergence is powerful. Any single observation might be questioned. But when many observations from different domains all point to the same conclusion, confidence grows. Dark matter is not speculative hypothesis, but well-established component of cosmological standard model. We may not know what it is, but we know with certainty that it exists and profoundly affects the universe. The challenge is detecting dark matter directly through its non-gravitational properties, if any exist. Dark matter doesn't just hold individual galaxies together, it creates the large-scale structure of the universe, a vast cosmic web spanning billions of light-years. If you could see dark matter, the universe would look like a three-dimensional spiderweb stretching across space. Dense filaments connect massive nodes where galaxy clusters reside. Between filaments lie vast voids, regions with little matter. This cosmic web structure traces dark matter's distribution. Visible galaxies are merely tracers lighting up the underlying dark matter scaffolding. How did this structure form? The story begins in the very early universe, shortly after the Big Bang. At that time, matter was distributed almost uniformly. But tiny density variations existed, 1 part in 100,000. Photons interacted strongly with ionized matter, preventing it from collapsing under gravity. But dark matter, not interacting with photons, wasn't affected by radiation pressure. It could collapse freely under its own gravity. Dark matter fell into the gravitational potential wells created by initial density variations. It formed dense clumps and filaments, creating gravitational potential wells that would later attract ordinary matter. After recombination, about 380,000 years after Big Bang, ordinary matter became neutral. Neutral atoms don't interact strongly with photons. Radiation pressure ceased supporting ordinary matter against gravity. Ordinary matter then fell into the gravitational potential wells that dark matter had already created. Galaxies formed where dark matter was densest. The visible universe traces the invisible dark matter distribution. This explains why galaxies aren't randomly distributed but follow the cosmic web pattern. Computer simulations starting with observed CMB fluctuations and including dark matter produce cosmic web structures matching observations. Without dark matter, simulations fail. Structure wouldn't have time to form by present day. Dark matter's head start collapsing before ordinary matter could was essential for structure formation on observed timescales. The cosmic web is thus dark matter's architecture. Visible matter decorates this structure but doesn't create it. Galaxy clusters form at web nodes, intersections of multiple filaments where dark matter and ordinary matter are most concentrated. These clusters are the largest gravitationally bound structures in the universe, containing thousands of galaxies. Filaments connect clusters, channeling matter and galaxies along preferred directions. Galaxies and gas flow along filaments toward clusters, feeding cluster growth over cosmic time. Voids, the empty regions between filaments, expand as matter drains toward filaments and clusters. Some voids reach hundreds of millions of light-years in diameter, containing very few galaxies. The cosmic web is not static. It evolves as gravity continues pulling matter into denser regions. Clusters grow more massive over time. Filaments become more defined. Voids expand. But the basic web pattern was established early, determined by initial density variations and dark matter's gravitational dominance. Observing the cosmic web reveals dark matter's distribution. Where galaxies concentrate, dark matter concentrates. Where galaxies are sparse, dark matter is sparse. The correlation is strong and consistent. The cosmic web's existence and properties provide independent evidence for dark matter. Its large-scale structure cannot be explained by visible matter alone. Dark matter is required. Understanding cosmic structure requires understanding dark matter. The two are inextricably linked. The visible universe we observe is just the illuminated portion of vast dark matter web. Most of the structure is invisible, detectable only through its gravitational effects on visible matter. This web is what holds everything together at the larger scales. Dark matter provides gravitational framework organizing visible matter. Understanding dark matter requires eliminating candidates, determining what it cannot be before identifying what it might be. The first question: could dark matter be ordinary matter that simply isn't glowing? Perhaps dust, planets, dead stars, or black holes. Ordinary matter, made of protons, neutrons, and electrons, is called baryonic matter in cosmology. Could there be enough non-luminous baryonic matter to account for dark matter? Early speculation suggested this possibility. Brown dwarfs, failed stars too small to sustain fusion, were considered. Perhaps space is filled with countless brown dwarfs we cannot see. Machos, massive compact halo objects, was the term for such candidates. Black holes, neutron stars, white dwarfs, brown dwarfs, rogue planets. Surveys searched for MACHOS through gravitational microlensing. When a MACHO passes in front of a distant star, it briefly magnifies the star's light. These surveys found some MACHOS, confirming they exist, but not nearly enough to account for dark matter. But neutrinos move at nearly light speed. They're too fast to explain observed structure. Hot dark matter would erase small-scale structure. It produces large structures, but not galaxies. Observations show structure exists at all scales, from galaxies to clusters to cosmic web. This requires particles moving slowly enough to allow small-scale structure formation. Neutrinos, being hot dark matter, cannot be the primary component. Dark matter must be cold. Could dark matter be black holes formed in early universe, primordial black holes? Unlike stellar black holes formed from collapsed stars, primordial black holes would form from density fluctuations shortly after Big Bang. They could have various masses, potentially avoiding some constraints on Machos. But microlensing surveys and other observations constrain primordial black holes across wide mass ranges. There's not enough primordial black holes to be dark matter unless they're in specific narrow mass ranges. Recent interest has revived this idea for certain mass ranges, but it remains less favoured than particle dark matter. Could dark matter be modifications to gravity rather than new matter? MODIFIEDNE.TONIAN DYNAMICS MOND proposes that gravity behaves differently at very low accelerations. MOND can explain galaxy rotation curves without dark matter by changing gravitational law. But MOND struggles with galaxy clusters, gravitational lensing, and cosmological observations. No single modified gravity theory explains all dark matter evidence convincingly. Most physicists favour particle dark matter over modified gravity. Though research continues on both. Could dark matter be something even more exotic? Primordial black holes, exotic particles, modifications to fundamental physics. Many proposals exist. Dark matter could be axions, WIMPs, sterile neutrinos, or something not yet conceived. What we know definitively is what dark matter is not. It's not ordinary matter in sufficient quantity. It's not hot relativistic particles like ordinary neutrinos. It's not easily explained by modifying gravity. Dark matter must be cold, non-baryonic, and non-relativistic. It must interact very weakly with ordinary matter and itself. These constraints guide the search for dark matter's identity, narrowing possibilities while leaving fundamental nature uncertain. Having established what dark matter is not, we can explore what it might be. The leading candidates proposed by particle physics, WIMPs, weakly interacting massive particles, are perhaps the most studied candidates. WIMPs would interact through gravity and weak nuclear force, but not through electromagnetic or strong forces. This makes them nearly invisible. They would pass through ordinary matter like ghosts, occasionally interacting weakly. The weak force has very short range. WIMPs would need to come extremely close to atomic nuclei to interact noticeably. WIMPs with masses between 10 and 10,000 times the proton mass naturally produce observed dark matter abundance through thermal production in early universe. This quote 3 makes them theoretically attractive. The math works out naturally without fine-tuning. Supersymmetry, an extension of the standard model, predicts stable massive particles that could be WIMPs. The lightest supersymmetric particle, neutralino, is natural WIMP candidate if supersymmetry is correct. Sterile neutrinos with masses of a few kilo electron volts could comprise dark matter. Some X-ray observations have shown anomalous lines that might be sterile neutrino decay, but evidence remains inconclusive. Primordial black holes have regained attention recently. If they formed in early universe with specific mass ranges, they might be dark matter. Recent gravitational wave detections of merging black holes with unexpected masses have renewed interest, but constraints from various observations limit primordial black holes' contribution to dark matter. They probably aren't the dominant component, though they might contribute partially. More exotic proposals include asymmetric dark matter, hidden sector particles, or even entire dark sector with its own complex physics. Asymmetric dark matter would be matter with no corresponding antimatter, explaining why dark matter wasn't annihilated in early universe. Hidden sector particles would interact through forces we haven't discovered, creating entire dark matter physics parallel to ordinary matter physics. These possibilities remain speculative. Without detection, we cannot determine which, if any, is correct. The search for dark matter's identity is one of physics' greatest challenges. We know it exists, but not what it is. This situation is scientifically fascinating. Observations demand new physics beyond the standard model. Whatever dark matter is, discovering it will revolutionize particle physics and cosmology. It represents most of universe's matter. Understanding it is essential for understanding reality. The leading candidates, WIMPs and axions, continue to be searched for with increasingly sophisticated experiments. Future detectors might finally achieve first direct detection, revealing dark matter's nature. Or perhaps dark matter is something completely unexpected, requiring new theoretical frameworks we haven't yet developed. The mystery deepens with each non-detection, constraining possibilities while leaving fundamental nature uncertain. Dark matter isn't just an exotic phenomenon in distant galaxy clusters. It's here, in our galaxy, surrounding us, holding the Milky Way together. The Milky Way is a spiral galaxy containing several hundred billion stars in a rotating disk. Our solar system orbits the galactic centre at about 220 kilometers per second, taking about 230 million years to complete one orbit. This orbital velocity reveals how much mass lies within our orbit. Using Newton's laws, we can calculate the gravitational pull needed to maintain this speed. The visible matter in stars, gas and dust within our orbit is insufficient to provide necessary gravitational pull. We should be orbiting more slowly if only visible matter existed. Or alternatively, we should have escaped the galaxy entirely, but we're still here, orbiting steadily. Additional invisible mass provides the extra gravitational pull. The Milky Way's rotation curve, like other spirals, remains flat at large distances from centre. Stars and gas clouds far from galactic centre orbit just as fast as those closer in. This indicates dark matter halo extending far beyond visible disk, perhaps 200,000 light-years in radius or more. The halo is roughly spherical, unlike the flattened disk of visible stars and gas. We're embedded within this dark matter halo. Dark matter particles are passing through Earth, through this room, through your body right now. But they interact so weakly that they pass through without effect. You're transparent to dark matter, and it's transparent to you. Estimates suggest millions of dark matter particles pass through every square centimetre every second. Yet we don't notice. Their interactions are so rare that despite huge numbers, detectable collisions are extremely uncommon. This is why direct detection is so difficult. Even with large detectors and long observation times, events are rare. The local dark matter density near Earth is estimated at about 0.3 giga-electron-volts per cubic centimetre. This seems like a lot, but it's actually incredibly diffuse. It's equivalent to 1 proton mass per several cubic centimetres. For comparison, air at sea level has about 10 to the 19th molecules per cubic centimetre. Dark matter is far more diffuse than air. It's nearly a perfect vacuum by ordinary standards. Yet collectively, all this diffuse dark matter throughout the galaxy outweighs visible matter by a factor of perhaps 6 to 1. The dark matter halo's gravitational pull shapes the Milky Way's structure and evolution. It provides gravity that keeps the disk stable. Without it, the disk would become unstable and disperse. The halo also captures smaller galaxies that venture too close. These satellite galaxies orbit the Milky Way, eventually merging with it. The Magellanic Clouds, small galaxies visible from southern hemisphere, are satellites of the Milky Way. They orbit within our dark matter halo, gradually losing mass to the Milky Way through tidal interactions. Eventually they'll merge completely, their stars joining the Milky Way. This process is ongoing throughout cosmic history. Galactic mergers are common. Most large galaxies grow by consuming smaller ones. Dark matter halos merge during these interactions. The larger halo dominates, incorporating the smaller galaxy's dark matter. Computer simulations of galaxy mergers require including dark matter. Without it, simulations don't match observations. The Milky Way's dark matter halo probably contains substructure, clumps and streams from past mergers. These subhalos might host small satellite galaxies, or might be dark satellites without significant visible matter. Detecting dark matter substructure is active research area. It could provide clues about dark matter's properties. Understanding our galaxy requires understanding its dark matter halo. The two are inseparable. The halo provides gravitational foundation. The visible galaxy is just the illuminated tip of much larger dark matter structure. Dark matter doesn't just hold galaxies together after they form, it's essential for their formation in the first place. Without dark matter, galaxies as we know them wouldn't exist. The universe would be fundamentally different. Galaxy formation begins with dark matter. In early universe, dark matter's gravity created potential wells. These potential wells were regions where dark matter was slightly denser than average. As mentioned earlier, dark matter could collapse gravitationally before ordinary matter, because it wasn't affected by radiation pressure. By the time ordinary matter became neutral and could collapse, dark matter had already created deep gravitational wells. Ordinary matter, mostly hydrogen and helium gas, fell into these wells, attracted by dark matter's gravity. The gas accumulated at the bottoms of potential wells, becoming denser and beginning to form structures. As gas accumulated, it cooled by radiating energy. Cooling allowed it to condense further. Eventually, gas became dense enough for gravitational collapse to form stars. The first stars ignited. Dark matter provides necessary gravitational scaffolding. It creates conditions for gas to accumulate and stars to form. Different dark matter properties would produce different galaxy properties. If dark matter were hot instead of cold, only huge structures would form. No galaxies, only enormous diffuse clouds. If dark matter interacted strongly with itself, halo shapes would differ, affecting galaxy structure. Observed galaxy properties constrain dark matter's properties. Dark matter must be cold and nearly collisionless to match observations. Understanding why galaxies look the way they do requires understanding dark matter's role. Galaxy morphology, rotation, mass distribution all connect to underlying dark matter halo properties. The visible galaxy is shaped by invisible halo. We cannot fully understand what we see without accounting for what we cannot see. At the largest scales, dark matter's influence becomes even more dramatic, organizing matter into cosmic web and forming massive galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies, all orbiting within a massive dark matter halo. The Coma cluster, where dark matter was first inferred, contains over 1,000 galaxies in a region a few million light-years across. Cluster masses range from 10 to the 13th to 10 to the 15th solar masses. Most of this mass, about 85%, is dark matter. Visible stars comprise only about 2%. The remaining 13% is hot intracluster gas, heated to millions of degrees by falling into the cluster's potential well. This gas emits X-rays, making clusters bright X-ray sources. X-ray observations reveal the gas distribution. The gas temperature indicates the depth of the gravitational potential well. Hotter gas requires deeper well, meaning more mass. Observations consistently show that total mass far exceeds visible mass, requiring enormous dark matter halos. Gravitational lensing by clusters provides independent mass measurements. Background galaxies appear distorted around clusters. The distortion pattern reveals the cluster's total mass distribution. Strong lensing creates dramatic arcs and multiple images. Weak lensing creates subtle shape distortions measurable statistically across many background galaxies. Both techniques show that clusters contain far more mass than visible, distributed smoothly around the cluster. The mass distribution matches what we'd expect for dark matter halo with embedded galaxies and gas. The bullet cluster, mentioned earlier, provides spectacular evidence for dark matter's existence and properties. The collision separated hot gas from dark matter, creating spatial offset between visible matter and gravitating mass. Gravitational lensing maps show that most mass, the dark matter, passed through the collision unimpeded. The gas, being ordinary matter, interacted and slowed down. The galaxies and dark matter continued through. This natural experiment demonstrates dark matter's collisionless nature. It doesn't interact with itself or ordinary matter except gravitationally. Clusters form at nodes in the cosmic web where multiple filaments intersect. Dark matter is most concentrated at these nodes. Galaxies and gas flow along filaments toward clusters. Clusters grow over cosmic time by accreting matter from surroundings and by merging with other clusters. Cluster mergers are among the most energetic events since the Big Bang. When massive clusters collide, their combined mass exceeds 10 to the 15th solar masses. The kinetic energy is enormous. Gas heats to tens of millions of degrees, emitting brilliant X-rays. Dark matter halos pass through each other, gradually merging through gravitational interaction. These mergers reveal dark matter's properties. Observations constrain how much dark matter can self-interact. If dark matter interacted strongly with itself, halos couldn't pass through cleanly. They'd be disrupted or delayed. Observations show clean passage, indicating very weak or zero self-interaction. Dark matter is nearly perfectly collisionless. Beyond clusters, dark matter shapes the entire cosmic web. Simulations starting with dark matter. Particles evolving under gravity reproduce the web structure. Filaments form where dark matter streams converge. Voids form where dark matter is depleted. The observed galaxy distribution follows the dark matter distribution predicted by simulations. This agreement between dark matter simulations and observations is one of modern cosmology's great successes. It demonstrates that we understand large-scale structure formation despite not knowing dark matter's microscopic identity. Dark matter's gravitational behavior is well characterized. Its role in structure formation is understood. What remains mysterious is its fundamental nature. What particles comprise it? How are they created? But its cosmic role is clear. Dark matter is the architect of large-scale structure, organizing matter across billions of light years. To understand how dark matter came to dominate the universe, we must explore its thermal history in the early universe. Shortly after the Big Bang, the universe was extremely hot and dense. Everything existed as a primordial plasma. In this plasma, all particle species were in thermal equilibrium, constantly created and annihilated through particle interactions. This includes dark matter particles, if they interacted through any force beyond gravity. As the universe expanded and cooled, different particle species quote 5 of equilibrium at different times. Freeze-out occurs when a particle's interaction rate becomes slower than the universe's expansion rate. Once frozen out, a particle species no longer maintains thermal equilibrium. Its abundance becomes fixed. For WIMPs, freeze-out occurred when the universe was about 100 times cooler than WIMP mass. At this point, WIMPs were still relativistic or becoming non-relativistic. This production mechanism depends on mixing angles and sterile neutrino mass. For specific parameters, right abundance to be dark matter could be produced. All viable candidates must explain observed dark matter abundance. This is strong constraint on models. If a candidate overproduces dark matter, the universe would have too much dark matter, contradicting observations. If it underproduces, something else must provide the rest. Complicating the theory. The thermal history also affects dark matter's phase space distribution, its velocities and spatial distribution. Cold dark matter, produced with low velocities, remains cold throughout cosmic history. This allows structure formation on small scales. Cold dark matter can clump into galaxy mass halos. Hot dark matter, produced relativistically, washes out small-scale structure. Neutrinos are hot dark matter. They cannot explain observed structure at all scales. Dark matter must be cold or at most warm. This constrains production mechanisms and particle masses. Understanding dark matter's thermal history helps predict its current properties and potential signals. If WIMPs are dark matter, their relic abundance determines current density and thus detection rates in experiments. If axions are dark matter, their production mechanism determines mass range and coupling strength to ordinary matter. These predictions guide experimental searches. Knowing what to look for depends on understanding thermal history. The early universe was a particle physics laboratory at energies we cannot reach in colliders. Dark matter particles were created in this laboratory. Their current properties reflect these extreme conditions. By studying dark matter now, we learn about the early universe's physics. This connection between cosmology and particle physics is profound. Cosmological observations constrain particle physics beyond standard model. Dark matter is messenger from the early universe, carrying information about conditions shortly after the Big Bang. Understanding its thermal history is understanding a crucial chapter in cosmic history. The cosmic microwave background, radiation from when the universe became transparent, encodes crucial information about dark matter. CMB observations have become a precision tool for measuring dark matter's properties and abundance. The CMB also reveals that dark matter was cold, non-relativistic at recombination. Hot dark matter would erase small-scale fluctuations. The CMB shows fluctuations at all observable scales. This requires cold dark matter. The CMB thus independently confirms dark matter must be cold. CMB polarization provides additional information. Polarization patterns encode details about early universe physics. B-mode polarization, if detected from inflation, would tell us about extremely early universe. E-mode polarization, already measured, provides complementary constraints on cosmological parameters. Dark matter affects polarization through its gravitational influence on photon distribution. Precise polarization measurements refine dark matter, abundance determinations, and test cosmological models. CMB observations also reveal something profound. Dark matter and ordinary matter were never in thermal equilibrium with each other. If they had been, the effects would appear in CMB. Observations rule out strong coupling. Dark matter has been separate populations since very early times, interacting with ordinary matter only gravitationally. This separation explains why dark matter remains dark. It never coupled to photons strongly enough to emit or absorb light. The CMB thus provides crucial evidence for dark matter's existence and properties. Its observations are consistent with all other dark matter evidence from galaxies, clusters, and large-scale structure. This consistency across independent observations makes dark matter conclusion robust. The CMB is a snapshot of universe at 380,000 years, encoded information about even earlier times. Dark matter's gravitational effects on matter and radiation in those early times left imprints we observe today. By studying these imprints, we learn about dark matter despite its invisibility. Scientists are not content merely inferring dark matter's existence through gravitational effects. They want to detect it directly, to catch dark matter particles in the act of interaction. Direct detection experiments search for dark matter particles scattering off atomic nuclei in laboratory detectors. If dark matter particles, perhaps WIMPs, pass through matter, they occasionally collide with nuclei. Such collisions would transfer tiny amounts of energy, perhaps a few hundred kilo electron volts, to the nucleus. The nucleus recoils slightly. Detecting this recoil would be direct evidence of dark matter-particle interaction. The challenge is immense. Dark matter interacts so weakly that collisions are extraordinarily rare. In a kilogram of detector material, we might expect only a few dark matter interactions per year. Background radiation from cosmic rays, natural radioactivity, and other sources would overwhelm such rare signals. Either dark matter is not WIMPs, or WIMPs interact even more weakly than typical weak force predictions, or dark matter is lighter than expected. Future experiments will probe deeper. Xenont, Lux Zeppelin, and next-generation detectors will have even better sensitivity. They'll explore remaining parameter space. If WIMPs exist in accessible range, these experiments should find them. Direct detection remains one of our best hopes for identifying dark matter. A definitive signal would revolutionize physics. It would confirm dark matter's particle nature and begin revealing its properties beyond just gravitational effects. Until then, the search continues with patient, careful experiments, probing ever more sensitively into the dark matter mystery. Another approach to detecting dark matter exploits a dramatic possibility. Dark matter particles might annihilate with each other, producing observable radiation. If dark matter is its own antiparticle, or if dark matter and anti-dark matter both exist, they can annihilate when they meet. Annihilation would convert dark matter mass into energy, producing standard model particles, photons, neutrinos, or matter-antimatter pairs. These annihilation products could be detected with telescopes and detectors, providing indirect evidence of dark matter. The annihilation rate depends on dark matter density. Where dark matter is densest, annihilations occur most frequently. The galactic centre of our Milky Way, has very high dark matter density. It's a prime target for indirect searches. If WIMPs annihilate, they might produce gamma rays, high-energy photons detectable with space telescopes. The Fermi Gamma Ray Space Telescope has searched for gamma ray signals from galactic centre and elsewhere. Some observations show an excess of gamma rays from galactic centre region. The second quote, 6. This excess might be dark matter annihilation, or it might be unresolved astrophysical sources like millisecond pulsars. The interpretation remains debated. The signal properties don't definitively match either dark matter or pulsars. More data and better understanding of galactic centre astrophysics are needed to clarify the excess's origin. Dwarf spheroidal galaxies are another target. These small satellite galaxies of the Milky Way are dark matter dominated. They contain few stars and little gas. Most mass is dark matter. This makes them cleaner targets. Astrophysical backgrounds are lower than at galactic centre. Searches in dwarf galaxies have found no convincing dark matter signal, but they provide strong constraints on annihilation rates. These constraints complement direct detection limits, probing different aspects of dark matter interactions. Antimatter in cosmic rays provides another search avenue. If dark matter annihilates, it might produce antimatter particles. Positrons, anti-electrons, from dark matter annihilation would diffuse through galaxy, eventually reaching Earth. The positron fraction in cosmic rays has been measured with increasing precision. Some experiments found more positrons than expected. The Pamela satellite and AMS experiment on International Space Station measured excess positrons at high energies. This could be dark matter annihilation signal, or it could be positrons from pulsars or other astrophysical sources. Again, interpretation is ambiguous. Astrophysics can potentially explain observations without dark matter. Antiprotons have also been measured. Unlike positrons, antiprotons show no clear excess. This constrains dark matter models. If dark matter annihilates to quarks, it should produce both positrons and antiprotons. Positron excess without antiproton excess is puzzling. This might mean dark matter annihilates preferentially to leptons, not quarks, or it might mean positrons aren't from dark matter. Neutrino telescopes search for dark matter annihilation in the Sun or Earth's centre. Dark matter particles could accumulate in these bodies through gravitational capture. Once captured, they'd sink to the centre where density is highest. There, they'd annihilate, producing neutrinos. High-energy neutrinos from Sun or Earth would be smoking gun signal of dark matter annihilation. IceCube, a cubic kilometre neutrino detector at South Pole, has searched for such signals. No excess neutrinos from Sun or Earth have been detected. This sets limits on dark matter annihilation and scattering rates. Indirect detection is complementary to direct detection. Each probes different aspects of dark matter properties. Direct detection measures dark matter scattering on nuclei. Indirect detection measures annihilation into standard model particles. Together, they constrain dark matter's interaction strengths with ordinary matter. The lack of definitive signals in either direct or indirect searches is humbling but informative. Dark matter interacts weakly enough that even sophisticated experiments haven't detected it. This pushes the field toward more sensitive experiments and broader search strategies. Perhaps dark matter doesn't annihilate significantly. Perhaps it's too light for current experiments. Perhaps it's something unexpected. The searches continue, driven by confidence that dark matter exists and hope that it will eventually reveal itself. Particle colliders like the Large Hadron Collider offer another approach, producing dark matter particles directly in high-energy collisions. If dark matter is a particle with mass accessible to colliders, collisions might create dark matter particles along with standard model particles. The LHC collides protons at energies of 13 trillion electron volts, recreating conditions like those in early universe. In these collisions, if dark matter particles have masses below a few trillion electron volts, they could be produced. Dark matter particles wouldn't interact with detectors. They'd escape invisibly, carrying away energy and momentum. This missing energy would signal their presence. Detectors measure all visible particles and reconstruct the collision. If energy and momentum don't balance, something invisible was produced. This missing energy could be dark matter. The challenge is distinguishing dark matter signals from standard model backgrounds that also produce missing energy. Neutrinos, for instance, are produced in many collisions and escape undetected, creating missing energy. Sophisticated analysis techniques are needed to separate potential dark matter signals from neutrino backgrounds. Searches at LHC have looked for various signatures: missing energy plus photons, missing energy plus jets, missing energy plus heavy particles. Different production mechanisms would create different accompanying particles along with dark matter. Supersymmetry predicts specific production channels and particle signatures. Searches have targeted these predictions. Despite extensive searching through years of LHC data, no convincing dark matter production has been observed. This doesn't mean dark matter isn't particles. It means if dark matter particles exist, they're either too massive for LHC energies, or they're produced too rarely, or production mechanism is unexpected. The LHC has excluded many supersymmetric dark matter models. Large regions of parameter space are now ruled out. This has pushed theorists toward more complex models or different dark matter candidates. Future colliders might reach higher energies. Proposed machines could access heavier masses. The International Linear Collider, if built, would collide electrons and positrons with different collision characteristics than LHC. This might enable better searches for certain dark matter signatures. A future circular collider, proposed for construction after LHC, would reach even higher energies, exploring new mass ranges. These future machines might finally produce dark matter particles. If they exist within accessible mass ranges, collider searches complement astronomical observations and direct detection experiments. Colliders probe dark matter's particle physics properties, mass, production mechanisms, decay channels. Observations probe gravitational effects and cosmological implications. Together they provide comprehensive search strategy covering different aspects of dark matter. The lack of collider signals, combined with no direct or indirect detection, paints a picture of dark matter more elusive than anticipated. Simple WIMP models predicted signals should have been seen by now. Their absence requires explanation. Either dark matter is not WIMPs, or it interacts even more weakly, or its mass is outside expected range. This is frustrating but also intellectually exciting. Nature is teaching us that reality is more complex than our theories suggested. Dark matter might be something we haven't imagined yet. The search pushes us toward new ideas. Perhaps dark matter is in hidden sector, interacting through new forces we haven't discovered. Perhaps it's asymmetric dark matter without antiparticles, explaining why annihilation signals aren't seen. Perhaps it's ultralight axions, too light for colliders but detectable through other means. The null results from colliders help narrow possibilities, guiding theoretical development. As experiments exclude parameter space, remaining possibilities become clearer. Eventually either we'll detect dark matter through one of these methods, or we'll be forced to radically rethink our approach. Both outcomes would advance understanding. Detection would revolutionize physics. Non-detection with complete coverage would force new paradigms. The search continues across multiple fronts: colliders, direct detection, indirect detection, and astronomical observations. This multi-pronged approach maximizes chances of eventual discovery while teaching us about dark matter's properties through exclusion. While particle dark matter is the leading explanation for missing mass, alternative theories exist that attempt to explain observations without invoking new particles. The most prominent alternative is modified Newtonian dynamics, MOND, proposed by Mordechai Milgrom in 1983. MOND suggests that Newton's and Einstein's gravity laws are not precisely correct at very low accelerations. In standard physics, Newton's second law, force equals mass times acceleration, holds at all accelerations. MOND proposes modification at accelerations below a critical value, about 10 to the minus 10 meters per second squared. At these tiny accelerations found in galaxy outskirts, gravitational force falls off more slowly than inverse square law predicts. This modification could explain flat galaxy rotation curves without dark matter. Outer stars experience low accelerations. MOND's modified gravity gives them extra force, speeding their orbits to observed values. MOND successfully fits many galaxy rotation curves with single parameter. This is impressive. It predicts specific relationship between visible mass distribution and rotation curve shape. This prediction, the Tully-Fisher relation connecting galaxy luminosity to rotation velocity, is well verified observationally. MOND's success with galaxy rotation curves makes it worth considering seriously. However, MOND faces significant challenges. It struggles to explain observations beyond galaxies, galaxy clusters for instance. Require more missing mass than MOND provides even with its modification. The bullet cluster is particularly problematic for MOND. The separation of mass from visible matter seems to require dark matter particles. MOND is non-relativistic theory. Extending it to relativistic framework consistent with general relativity is difficult. Several relativistic theories based on MOND ideas have been proposed, Tevis, Emog and others. These theories add tensor, vector, and scalar fields to Einstein's equations, modifying gravity in specific ways. But these theories are complex, with multiple parameters requiring tuning. They lack the elegance of general relativity. More fundamentally, they struggle with cosmology. Explaining CMB observations and structure formation without dark matter is extremely difficult. The CMB acoustic peaks encode specific matter content. MOND-based theories have trouble reproducing observed power spectrum. Large-scale structure simulations with modified gravity don't match observations as well as dark matter simulations. MOND works well for galaxies but fails at larger scales. This is suspicious. Why would gravity modification work at galaxy scales but not cluster and cosmological scales? Dark matter, in contrast, explains observations consistently across all scales from galaxies to cosmic web. This consistency favours dark matter over modified gravity. Most physicists conclude that while MOND is interesting and worth studying, it's probably not the correct explanation. Dark matter provides simpler, more comprehensive explanation for wider range of phenomena. However, modified gravity research continues. Perhaps there's kernel of truth in MOND at galaxy scales. Maybe both dark matter and some gravitational modification exist. This would be surprising, but not impossible. Some recent work explores this possibility, combining dark matter with modified gravitational sector. These hybrid theories might explain MOND's success with galaxies, while addressing its failures at larger scales. But added complexity makes them less attractive theoretically. Occam's razor favours simpler dark matter explanation. The debate between dark matter and modified gravity is healthy for science. It forces proponents of each to address weaknesses. Dark matter must explain why MOND works so well for galaxies. Modified gravity must explain large-scale observations. This mutual pressure strengthens both approaches, leading to better theories. For now, overwhelming evidence favours dark matter. But science remains open to alternatives if compelling evidence emerges. The search for dark matter continues while modified gravity research explores parameter space for viable alternatives. Whichever explanation is correct, the underlying phenomena, flat rotation curves, gravitational lensing, structure formation, are real and demand explanation. We will eventually understand what holds galaxies together, whether through dark matter particles modified gravity, or something completely unexpected. The search for dark matter continues with new experiments, improved technologies, and innovative approaches promising breakthroughs in coming decades. Next-generation direct detection experiments will be significantly more sensitive than current generation. Lux Zeppelin, or LZ, uses 7 tons of liquid xenon in underground laboratory in South Dakota. This detector began operating recently and will search for WIMPs over several years with unprecedented sensitivity. Xenon T in Italy and Pandax 4T in China also use multi-ton xenon detectors with excellent sensitivity. Together, these experiments will explore remaining WIMP parameter space. If accessible WIMPs exist, they should find them. If not, they'll have covered most reasonable WIMP models. Forcing community to consider alternatives. Axion searches are also advancing. The Axion Dark Matter Experiment, ADMX, uses resonant cavities in strong magnetic fields. Axions converting to photons in the magnetic field produce signals at specific frequencies. ADMX is systematically scanning through possible axion masses, gradually covering parameter space. Other axion experiments use different technologies: helioscopes looking for solar axions, light shining through walls, experiments testing axion-photon conversion. IAXO, International Axion Observatory, is planned as next-generation helioscope with much improved sensitivity. These experiments might detect axions in coming years if they comprise dark matter. Gravitational waves provide entirely new approach. Dark matter clumps could produce gravitational wave signals. LIGO, Virgo and CACRA detect gravitational waves from black hole mergers. Future detectors might see dark matter signatures. If dark matter forms boson stars, compact objects made of axion-like particles, mergers could produce detectable signals. LISA, the space-based gravitational wave detector launching in the 2030s, will access different frequency ranges. It might detect gravitational waves from dark matter structures inaccessible to ground-based detectors. Astronomical surveys continue improving our understanding of dark matter's distribution and properties. The Vera Rubin Observatory, beginning operations soon, will survey entire visible sky repeatedly. It will discover thousands of new dwarf galaxies, providing targets for indirect detection searches. It will measure weak gravitational lensing by dark matter at unprecedented precision. Mapping dark matter distribution. Euclid Space Mission and Roman Space Telescope will measure dark matter through lensing and galaxy clustering. These missions will constrain dark matter's properties through large-scale structure observations. Improved CMB measurements might detect signatures of dark matter interactions in early universe. Next-generation CMB experiments might find subtle effects that constrain dark matter's properties beyond current limits. Particle physics will continue exploring beyond standard model. Future colliders, if funded and built, will search for dark matter at higher energies and with better precision. Theoretical work continues developing new dark matter models and prediction-testable signatures. The discovery space remains vast. Many possible dark matter candidates and detection methods exist. This diversity of approaches increases likelihood that dark matter will eventually be detected. When detection occurs, it will open an entirely new field of physics, dark matter physics. We'll measure dark matter's mass. Interactions perhaps even discover dark matter has complex structure. Maybe there's an entire dark sector with multiple particle types and dark forces. This would be comparable to discovering atomic physics, a whole new realm of reality to explore. Or perhaps dark matter will resist all detection attempts, remaining forever known only through gravity. This would be humbling but still scientifically valuable. We'd learn dark matter is truly dark, interaction-free except gravitationally. Either way, the coming decades promise progress, new experiments, new data, new insights. The mystery of what holds everything together will gradually yield to patient, systematic investigation. Dark matter is real, its effects are unmistakable. Eventually we will understand its nature. the future of dark matter research is bright. Perhaps ironically for studying darkness. To appreciate dark matter's importance, consider a thought experiment. What if dark matter didn't exist? How different would the universe be? Without dark matter, galaxy rotation curves would show declining velocities with distance from centre, as Newton's laws predict from visible matter. But this would mean galaxies couldn't exist as we know them. The outer stars would orbit too slowly to be gravitationally bound. Over time, these stars would escape, gradually dispersing the galaxy. Spiral arms would unwind and disappear. Galaxies would be much smaller, containing only stars tightly bound near the centre, where visible matter density is highest. Most stars we observe in galaxy outskirts wouldn't be there. They'd have drifted away over billions of years. The Milky Way itself would be far smaller. Our solar system, located in outer regions, might not be part of any galaxy. We'd be intergalactic nomads, drifting through void between small galactic cores. Galaxy clusters couldn't exist. The measured velocities of galaxies within clusters are too high for visible mass to bind them. Without dark matter, clusters would be temporary groupings. Galaxies would fly apart after brief interactions. The hot intra-cluster gas would escape. Nothing would hold it in the cluster's gravitational well. The bullet cluster collision wouldn't make sense. We observe most mass separated from visible matter. Without dark matter particles to separate cleanly from gas, the mass distribution would follow the gas. Gravitational lensing would match visible matter distribution, but observations show lensing mass far exceeds visible mass. This discrepancy couldn't be explained without dark matter or radical modification to gravity. Structure formation in early universe wouldn't work. Ordinary matter couldn't collapse to form galaxies before dark energy dominated. Radiation pressure supported ordinary matter until recombination. By the time it could collapse, cosmic expansion would be too fast. Dark matter collapsed earlier, creating potential wells that later captured ordinary matter. Without this, structure formation would be delayed or prevented entirely. The cosmic microwave background power spectrum would look completely different. Acoustic peaks depend on matter radiation ratio and total matter density. Without dark matter, only ordinary matter contributes. Peak heights and locations would shift dramatically. Observed CMB contradicts universe with only ordinary matter. Dark matter is required for consistency. The cosmic web wouldn't exist. Large-scale structure requires dark matter's gravitational scaffolding. Without it, matter distribution would be more uniform or structured completely differently. Galaxies, if they existed at all, would be randomly scattered, not organized into filaments and clusters. Planet formation might be affected. Heavy elements are produced in stars. If stars form less efficiently without dark matter enabling galaxy formation, heavy element abundance would be lower. This could affect planet formation and potentially the existence of rocky planets like Earth. Life as we know it requires heavy elements: carbon, oxygen, nitrogen, iron. These come from stellar nucleosynthesis. Fewer stars mean fewer supernovae producing and distributing heavy elements. Life might be impossible or far less common in universe without dark matter. This anthropic observation is striking. Dark matter isn't just cosmic curiosity, it's apparently necessary for our existence. Without dark matter creating conditions for galaxy formation, stellar evolution, and heavy element production, we wouldn't be here. The universe would be vastly emptier, simpler, and less interesting. Huge voids separated by tiny cores of stars. No grand spiral galaxies, no galaxy clusters, no cosmic web. Just isolated stellar knots in immense darkness. This thought experiment shows dark matter is an optional detail. It's fundamental to cosmic structure. Everything we observe depends on dark matter's gravitational influence, even though it remains invisible. We are quite literally products of dark matter. It shaped the cosmic environment that produced us. Understanding what holds everything together isn't an abstract academic question. It's understanding why we exist. Dark matter connects to deep questions about time, entropy, and the universe's evolution from past to future. The second law of thermodynamics states entropy always increases. This gives time its direction, the arrow of time. Dark matter plays a role in this cosmic entropy increase through structure formation and gravitational dynamics. In early universe, matter was nearly uniformly distributed. This represents low entropy configuration gravitationally. Gravitational entropy is counterintuitive. Uniform distribution has low gravity entropy. Clumped matter has higher entropy. This is opposite of ordinary entropy, where uniform is high entropy. Gravity is special because it's attractive. For gravitational systems, clumped configurations have more microstates, higher entropy than uniform distributions. Dark matter's gravitational collapse increased entropy. As it clumped into halos, cosmic gravitational entropy grew. This entropy increase is irreversible. Once collapsed, dark matter halos don't spontaneously disperse. The process has direction, from uniform to clumped, from lower to higher gravitational entropy. This contributes to universe's overall entropy increase, reinforcing time's arrow. Dark matter's collisionless nature affects entropy evolution. Unlike ordinary matter, dark matter doesn't dissipate energy through friction. Ordinary matter heats, radiates, cools, and settles into equilibrium configurations. Dark matter, lacking these interactions, maintains kinetic energy. Particles orbit in halos without dissipating. This creates different entropy evolution than purely dissipative systems. Dark matter halos reach virial equilibrium, balance between kinetic and potential energy, but don't collapse further. They maintain quasi-stable configurations over cosmic time, held by gravity and particle motion. These halos are maximum entropy states for collisionless gravitational systems of given energy and angular momentum. Once formed, they persist essentially unchanged unless disturbed by mergers. This quasi-equilibrium is unusual. Most physical systems eventually reach complete equilibrium and stop changing. Dark matter halos reach dynamical equilibrium, but remain structured, not maximally mixed. This reflects dark matter's special properties: collisionless, interacting only gravitationally. The late universe, dominated by dark matter halos, dark energy, and isolated galaxies, approaches a final state. In distant future after heat death, dark matter halos persist as cold, dark structures. They'll remain essentially unchanged for unimaginable timescales, barring proton decay or other exotic processes. If protons decay, ordinary matter in galaxies eventually disappears. Dark matter, if stable, outlasts everything else. The final universe is dark matter halos with nothing visible. This dark matter-dominated future represents maximum entropy gravitational configuration. Halos can't collapse further without dissipation. They can't expand without energy input. They sit in perpetual dynamical equilibrium, unchanging monuments to entropy increase. This final state is universe's gravitational destiny, shaped fundamentally by dark matter. Dark matter also connects to cosmological horizon problem and inflation. The horizon problem asks why distant regions of the universe have same temperature, despite never being in causal contact. Inflation solves this by proposing early exponential expansion that brought all observable regions into causal contact. Dark matter's distribution reflects conditions set during inflation. Its properties constrain inflationary models. If dark matter is axions, their abundance depends on inflation dynamics. Measuring dark matter constrains inflation. Similarly, if dark matter is produced during reheating after inflation, its properties reveal reheating physics. Dark matter is messenger from earliest universe. Carrying information about physical conditions then, understanding dark matter helps reconstruct cosmic history, tracing evolution from inflation through structure formation to present. The arrow of time, entropy increase, structure formation, and dark matter are deeply interconnected. Dark matter doesn't just hold things together spatially, it participates in temporal evolution, increasing entropy through gravitational collapse. It gives cosmic structure its history, its trajectory from simple to complex, and eventually back towards simplicity in far future. This temporal aspect of dark matter is often overlooked. We focus on its spatial distribution, but dark matter's evolution over time is equally important. It's dynamical, not static. Understanding what holds everything together requires understanding not just spatial structure, but temporal evolution. Dark matter shapes both space and time's arrow, both cosmic structure and cosmic history. If the multiverse exists, dark matter might vary across different universes, providing insight into our universe's special properties. In eternal inflation or string theory landscape scenarios, different universes have different physical laws and constants. Dark matter's properties might be different in other universes. Its abundance, particle type, or interactions could vary. This raises interesting questions. Is dark matter necessary for life? Do all life-compatible universes have dark matter? Our universe has dark matter. This might be a requirement for observers, an anthropic constraint. Without dark matter, structure formation fails. Galaxies don't form efficiently. Heavy elements might be scarce. These conditions seem unfavourable for life. Dark matter might be a necessary ingredient for habitability. If so, anthropic reasoning explains why we observe dark matter. We couldn't exist in universes lacking it. This doesn't tell us what dark matter is, but it suggests its existence isn't coincidental. The multiverse provides framework for understanding why our universe has its specific properties. Dark matter abundance in our universe is about 25% of critical density. Why this specific value? In multiverse, different universes have different abundances. We observe our value because it permits our existence. Too much dark matter might cause structures to collapse too readily. Galaxies might be too dense, stars too tightly packed. This could prevent planet formation or create environments inhospitable to life. Too little dark matter and structure formation is insufficient. Galaxies might not form at all. Our value might be typical of life-compatible range. Neither too much nor too little. This is speculative but illustrates how multiverse thinking connects to dark matter. If dark matter's properties vary across universes, observing our specific properties provides anthropic information. Dark matter in other universes might be completely different particles with different interactions. Maybe in some universes, what we call dark matter is actually visible. Their physics differs from ours. Or perhaps some universes lack dark matter entirely, relying on different structure formation mechanisms. These alternative universes would look vastly different from ours, possibly less structured or structured differently. The string theory landscape, with its 10 to 500th vacua, might include many dark matter possibilities. Different compactifications could produce different particle spectra, including different dark matter candidates. Our vacuum might be special in producing stable neutral particles that naturally become dark matter. Studying dark matter constrains which landscape vacua are realizable, narrowing possibilities. If we identify dark matter as specific particle predicted by specific beyond standard model theory, it suggests our vacuum has certain properties. This constrains landscape explorations, helping identify our universe's position in theory space. The anthropic principle also addresses fine-tuning concerns about dark matter. Dark matter properties seem well suited for structure formation. Is this fine-tuning requiring explanation? In multiverse, properties vary. We observe values compatible with observers. This explains apparent fine-tuning. Without multiverse, fine-tuning seems remarkable. Why are parameters just right? Design arguments emerge if multiverse is rejected and fine-tuning remains unexplained. But invoking multiverse has its own issues. It's untestable directly. Other universes are unobservable. Multiverse explanations for fine-tuning are controversial in philosophy of science. Some see it as giving up on deeper explanations. Others see it as natural consequence of fundamental theories. For dark matter specifically, multiverse reasoning suggests its existence and properties enable our existence. We wouldn't observe universe without dark matter because we couldn't exist there. This provides partial explanation for why dark matter exists, though not what it is. Understanding dark matter thus connects to deepest questions in cosmology and fundamental physics. It's not an isolated phenomenon, but part of a larger structure determining which universes are habitable. Whether multiverse reasoning is correct remains uncertain, but it provides interesting framework for thinking about dark matter. Dark matter might be random accident in our universe, or necessary feature of any universe with complex structure. Answering this requires understanding dark matter's nature and exploring theoretical landscape of possibilities. Dark matter raises profound philosophical questions about reality, observation, and the nature of scientific knowledge. Most of reality is invisible. We directly perceive only a tiny fraction of the universe's contents. This challenges naive realism, the idea that what we see is all there is. Science has always revealed hidden aspects of reality. Atoms, electromagnetic fields, quantum mechanics all extend beyond direct perception. But dark matter is an extreme case. It comprises 85% of matter and cannot be observed directly. We infer its existence purely through gravitational effects, never through direct interaction with our senses or instruments. This raises epistemological questions. How do we know dark matter exists if we can't observe it? The answer relies on inference to best explanation. Dark matter explains diverse observations simply and consistently. Alternative explanations like modified gravity are more complex and less successful. Scientific realism holds that successful theories approximately describe reality, even unobservable aspects. Dark matter is prime example. We believe it exists because the theory works despite invisibility. Instrumentalists might argue we shouldn't claim dark matter, quote 8, only that dark matter models work. This philosophical position treats theories as calculation tools, not claims about reality. But most scientists are realists about dark matter. It seems genuinely real, not merely convenient fiction. The convergence of evidence from independent observations makes reality claims strong. When multiple observation types, from rotation curves to lensing to CMB, all require same explanation, skepticism becomes difficult. Dark matter also illustrates how science reveals counterintuitive truths. That most matter is invisible violates common sense, yet evidence overwhelmingly supports it. Science often contradicts intuition. Earth orbits the sun despite appearances. Time is relative. Quantum mechanics is probabilistic. Dark matter continues this tradition. Reality is stranger than everyday experience suggests. This should make us humble about claims based on intuition alone. Nature doesn't conform to human preconceptions. Dark matter raises questions about substance and properties. What makes something matter? Traditionally, matter has mass, occupies space, and can be touched or observed. Dark matter has mass but can't be touched or directly observed. Does it count as matter? Some suggest, quote, 10, quote, is misnomer. Perhaps, quote, 11, quote, or quote 12, quote, better captures its nature. Or maybe our concept of matter needs expansion. Dark matter shows matter has properties beyond traditional definitions. Philosophically, dark matter resembles ancient concepts like ether, invisible substance pervading space. But unlike ether, dark matter has observational support. It's not speculative metaphysics, but empirically grounded science. This distinguishes modern dark matter from historical analogies. Evidence, not philosophy, drives acceptance. Dark matter also connects to underdetermination of theory by evidence. Multiple theories might explain same observations. Modified gravity and particle dark matter. both attempt explaining rotation curves and lensing. In principle, observations might not uniquely determine which theory is correct, but as evidence accumulates, alternatives become increasingly constrained. Dark matter consistently explains more phenomena. This suggests that underdetermination is practical challenge, not insurmountable philosophical problem. Eventually, sufficient evidence determines correct theory, even for unobservable entities. Dark matter illustrates successful scientific realism. Invisible entities can be scientifically established through systematic observation and inference. The success of dark matter in physics strengthens case for scientific realism generally. If we can be confident about invisible dark matter, we can be confident about other theoretical entities. Finally, dark matter reminds us that knowledge is hard-won. Understanding reality requires going beyond appearances. We must use sophisticated tools, mathematics, computer simulations, sensitive instruments, careful reasoning. Direct perception is limited. Intellectual exploration reveals reality's hidden depths. This epistemological lesson extends beyond dark matter. Much of reality operates beneath observation's surface. Science reveals this hidden reality patiently, systematically, building knowledge through evidence and theory. Dark matter stands as testament to science's power to reveal what we cannot directly see. Understanding dark matter affects how we think about humanity's place in the cosmos and the nature of our knowledge. The discovery that most matter is invisible is humbling. It reveals how much we don't directly experience. We evolve to perceive visible light, hear sound, feel pressure. These senses shaped our intuitions, but the universe consists mostly of things our senses cannot detect. We're blind to most of reality. This cosmic blindness should inspire intellectual humility. Our natural perceptions are severely limited. Only through science do we transcend these limitations, developing instruments and theories revealing hidden reality. Dark matter exemplifies this transcendence. We cannot see it, but we know it's there through reasoning. This demonstrates human cognitive power. We understand things beyond direct experience through abstract thought. The ability to infer invisible causes from visible effects distinguishes human intelligence. We look at rotating galaxies and deduce invisible matter. We observe gravitational lensing and calculate dark mass. This is remarkable achievement. We've discovered most of the universe despite its invisibility. Understanding dark matter also provides cosmic perspective on human significance. Everything we see, stars, planets, galaxies, is minority constituent. Most universe is unseen dark matter. The visible universe we admire is just a small fraction of total. We're privileged to live in luminous part, yet we're embedded in and depend on invisible majority. Dark matter shaped structures that enabled our existence. Without dark matter's gravitational scaffolding, galaxies wouldn't have formed. We wouldn't exist. Our existence is intimately tied to invisible processes and invisible matter. This connects to anthropic observations. We observe life-compatible universe because incompatible universes lack observers. Dark matter is apparently necessary for compatibility. Its presence enabled our existence. This doesn't mean universe was designed for us. It means only compatible universes produce us to observe compatibility. Still, the connection between dark matter and our existence is profound. We are products of dark matter's gravitational influence, shaped by processes we cannot directly perceive. Dark matter also illustrates limits of human knowledge. We know it exists, but not what it is. Decades of searching haven't revealed its identity. It remains mysterious despite its importance. This should temper overconfidence about human understanding. Some questions remain deeply puzzling. Yet we should also celebrate progress. From complete ignorance to detailed knowledge of dark matter's properties is significant achievement. We know its abundance, distribution, gravitational effects, and many constraints on its nature. This is substantial knowledge, even if complete understanding eludes us. The search for dark matter unites human curiosity across cultures and generations. Scientists worldwide collaborate on experiments and observations, sharing data and insights. This global enterprise reflects humanity's collective desire to understand reality. Dark matter is challenge that transcends national boundaries, ideological differences, and individual ambitions. It represents human species seeking knowledge about cosmos that birthed us. For non-scientists, dark matter offers opportunity to appreciate scientific discovery's grandeur. Understanding that most universe is invisible, that science reveals what we cannot see, inspires awe. The cosmos is far stranger and more wonderful than ordinary experience suggests. Dark matter enriches our picture of reality, adding depth and mystery to existence. It reminds us that there's always more to discover, more depth to explore. The universe hasn't revealed all its secrets. Future discoveries await. This prospect should excite and motivate. We live in an era of active discovery about fundamental reality. Dark matter's mystery is challenge for current and future generations. Solving it will be landmark achievement. When we finally understand what holds everything together, it will rank among humanity's greatest intellectual accomplishments. Until then, we work with what we know, building on past insights while pushing into unknown. This is human endeavour at its finest. Questioning, exploring, discovering, understanding. Dark matter embodies both our ignorance and our knowledge, our limitations and our capabilities. It shows us as we are, curious beings embedded in mysterious universe, capable of understanding far more than we can directly perceive. After exploring dark matter from many angles, it's valuable to summarize what we know with high confidence versus what remains uncertain. We know with certainty that dark matter exists. The evidence is overwhelming and comes from independent observations. Galaxy rotation curves consistently show velocities too high for visible matter alone. Gravitational lensing demonstrates mass far exceeding visible matter across all scales from galaxies to clusters. The bullet cluster shows mass separated from visible matter, smoking gun for particle dark matter. Cosmic microwave background observations require cold dark matter for consistency with acoustic peak measurements. Large-scale structure formation matches simulations including dark matter, but not simulations without it. All these observations converge on the same conclusion. Invisible matter dominates universe's gravitating mass. No single observation might be conclusive, but the convergence from independent methods is powerful evidence. We know dark matter's approximate abundance. It comprises about 85% of total matter, 26% of universe's energy. This is measured precisely from CMB and consistently inferred from structure formation. We know dark matter is cold, meaning it was non-relativistic when structures formed. Hot dark matter, like ordinary neutrinos, doesn't match observations. Cold dark matter is required. We know dark matter interacts gravitationally. This is how we detect it. Its gravitational effects are unmistakable. We know dark matter interacts very weakly, if at all, through electromagnetic strong and weak forces. It doesn't emit, absorb, or reflect light. Direct detection limits constrain possible weak interactions. We know dark matter is essentially collisionless. It doesn't self-interact significantly. The bullet cluster and other cluster collisions show dark matter passing through cleanly. We know dark matter forms extended halos around galaxies, far larger than visible stellar distributions. Rotation curves and weak lensing map these halos' density profiles. We know dark matter follows large-scale filamentary structure of cosmic web. Galaxy distributions trace underlying dark matter distribution consistently. These are established facts, well supported by observations and unlikely to be overturned. What remains uncertain is dark matter's identity. Is it WIMPs, axions, sterile neutrinos, primordial black holes, or something else? Despite decades of searching, No definitive detection of dark matter particles has occurred. This uncertainty is humbling. We know it exists, but not what it is. We don't know dark matter's exact distribution within galaxy halos. Density profiles in central regions are debated. Simulations predict cuspy halos with high central densities. Some observations suggest chord profiles with flatter centers. This cusp core problem might reflect missing physics in simulations or observational systematics. We don't know if dark matter has any non-gravitational interactions. It might be purely gravitational, or it might have extremely weak interactions we haven't detected. We don't know if dark matter is single particle type or multiple types. There might be dark matter sector with complex structure. We don't know if dark matter is stable or decays slowly. Decay would produce signals we haven't yet definitively observed. We don't know if dark matter relates to other unsolved problems in physics like matter-antimatter asymmetry or quantum gravity. These uncertainties motivate ongoing research. Experiments continue searching for direct signals. Observations continue refining dark matter's properties and distribution. Theorists continue developing models predicting testable signatures. The certainties provide foundation. Dark matter exists, has specific properties, plays crucial cosmic role. The uncertainties provide direction. We know what questions to address and how to search for answers. Science progresses by distinguishing known from unknown, certainty from speculation. For dark matter, we've made tremendous progress in understanding its role while still seeking its nature. This combination of knowledge and mystery makes dark matter fascinating scientifically. We know enough to be confident in its reality. We don't know enough to stop searching. The balance drives research forward. Established facts constrain possibilities. Remaining mysteries motivate exploration. Understanding what we know helps appreciate both progress achieved and challenges remaining. Dark matter is real. It holds everything together. Its nature awaits discovery. We live in a universe dominated by invisible matter. A reality with profound but subtle implications for daily existence. Dark matter particles likely pass through you constantly. Millions per second stream through every square centimetre, yet you don't notice. The interactions are so weak they have no perceptible effect. This is simultaneously ordinary and extraordinary. You're immersed in cosmic dark matter sea, completely unaware. Dark matter shaped the galaxy we inhabit. The Milky Way exists because dark matter provided gravitational framework. Without dark matter, Earth wouldn't exist. The galaxy wouldn't have formed. The sun wouldn't have material to coalesce from. We are literally products of dark matter's influence, even though we've never directly interacted with it. This dependence on invisible is philosophically interesting. Our existence depends on what we cannot see. It's a humbling reminder of how much operates beyond our awareness. Dark matter also affects universe's future. Its gravitational pull competes with dark energy's repulsion. Dark matter tries to slow expansion through gravitational attraction. Dark energy accelerates expansion. Currently, dark energy wins. Expansion accelerates, eventually isolating galaxies beyond each other's horizons. Dark matter cannot prevent this. Its gravity is insufficient to overcome dark energy. In far future, dark matter halos persist but become isolated. Each galaxy cluster becomes island universe. Life in such epoch, if any exists, would observe profoundly different universe than we do. Only local group galaxies would be visible. Rest of universe beyond observation receded past horizon. Dark matter would still be there, holding local structures together, but cosmic context would shrink. For now, we live in special time. Universe is mature enough for complexity, yet young enough for visibility. We can observe cosmic web, distant galaxies, and understand universe's large-scale structure. This observational opportunity is temporary, cosmically speaking. Future civilizations won't have same view. Understanding dark matter's role contextualizes our cosmic position. We're embedded in dark matter halo. orbiting galactic center within invisible gravitational scaffold. This scaffold, not visible stars, determines our orbital motion and galactic structure. If we could see dark matter, galaxy would look completely different. Vast glowing halo dwarfing visible disk. We'd be deep within luminous sphere of dark matter, with stellar disk as minor feature. This perspective shift, imagining visible dark matter, helps appreciate its dominance. What we see, stars and nebulae, are just tracers illuminating invisible majority. Living in dark matter-dominated universe means accepting that most reality is hidden. This challenges human preference for direct perception, but enriches understanding of nature's complexity. Science extends perception beyond natural senses. Through it, we know of dark matter despite invisibility. This knowledge doesn't change daily life practically, but profoundly affects worldview. Understanding universe composition, knowing most is invisible, inspires sense of mystery and wonder. Reality is deeper than appearances. Visible is tip of iceberg. Most remains hidden beneath surface. This metaphysical realization that most of reality is imperceptible affects how we think about existence. Perhaps other hidden aspects await discovery. Dark matter might be first of many invisible components, or perhaps dark matter is anomaly, most exotic hidden feature. Either way, its existence teaches us to expect surprises, to remain open to counterintuitive truths. For astronomy enthusiasts, dark matter adds depth to stargazing. Looking at Milky Way's band across night sky, you know visible stars are minority. Most mass is in invisible halo surrounding an interpenetrating visible disk. This knowledge enriches experience. You're seeing decorated skeleton, glimpsing structure's visible parts. For physicists and cosmologists, dark matter provides career-spanning challenge. Understanding what holds everything together motivates research across multiple fields. Particle physics, astrophysics, cosmology all contribute to dark matter question. Its unifying problem drawing together diverse expertise. For philosophers, dark matter exemplifies successful scientific inference, revealing unobservable reality. It validates scientific realism, confidence that theories describe actual reality even when unobservable, for everyone. Dark matter is a reminder of universe's mystery and science's power. We live surrounded by invisible that shaped our existence. Science reveals it despite its hiding. This is remarkable human achievement worth celebrating, even as mystery of its nature persists. Beyond scientific facts, dark matter has aesthetic and poetic dimensions worth contemplating as we rest. There's beauty in the idea that most universe is hidden. Reality has depth beyond surface appearances. Like an iceberg with most mass below water, cosmos has most substance in invisible realms. This hidden depth makes reality more interesting than if everything were visible and obvious. Mystery and wonder increase when we realize how much remains unseen. Dark matter invites imagination. We can picture invisible halos, gravitational scaffolds, cosmic architecture. Though we can't see it, we can visualize its effects, its distribution, its role. This imaginative engagement with the unseen is profound human capacity. We understand through mental models and metaphors even what we cannot directly perceive. Dark matter is like stage framework in theatre, invisible to audience but supporting entire performance. Without it, the show, visible cosmos, couldn't proceed, yet it remains backstage, hidden. This metaphor captures dark matter's essential role despite its invisibility. Or consider dark matter as cosmic glue, invisible adhesive holding structures together. Galaxies would fly apart without it, like objects without glue. The metaphor isn't perfect scientifically, but conveys dark matter's binding function. There's something almost spiritual about contemplating invisible that pervades everything. Not supernatural or mystical, but deeply mysterious in natural sense. The universe contains more than we see. This resonates with human intuitions about reality's depth. Many philosophical and religious traditions emphasize hidden aspects of reality beyond immediate perception. Dark matter, while purely physical, echoes these themes. There's grandeur in a universe dominated by the invisible. It suggests humility before nature's complexity. We are small beings in vast cosmos, perceiving tiny fraction of total reality. Yet we have capacity to understand far beyond perception through reason and science. This combination, vast hidden universe and human ability to comprehend it, is inspiring. The search for dark matter has poetic dimension. Scientists seeking to illuminate the dark, bringing hidden into light through knowledge even though it remains physically invisible. This quest for understanding, patient exploration of mystery, embodies human intellectual striving. Dark matter also provides metaphor for other hidden aspects of life. Much in human experience operates beneath conscious awareness. Subconscious thoughts, social dynamics, historical forces, like dark matter shaping cosmic structure invisibly, these hidden factors shape our lives. The parallel isn't scientific, but provides way to think about unseen influences. Recognizing dark matter's dominance might inspire appreciation for what we have. We exist in luminous minority, invisible matter organized into stars and planets. This is rare and precious. Most universe is dark and cold. We're privileged to exist in region where complexity and warmth allow life and consciousness. This gratitude for fortunate position in cosmos, this appreciation of being in luminous minority, enriches perspective. Dark matter reminds us that absence can be as important as presence. What's missing, what's not seen, shapes reality as much as what's visible. This philosophical point extends beyond physics. Absences and negatives matter. Silence matters in music. Empty space matters in art. What's unsaid matters in communication. Dark matter is cosmic version of this principle. What's not seen matters enormously. Finally, there's beauty in the mystery itself. Not knowing dark matter's nature preserves sense of wonder. Once identified, dark matter will be less mysterious. Understanding often replaces mystery with familiarity. For now, while search continues, dark matter retains mystique. This shouldn't make us less eager for discovery. Understanding deepens appreciation rather than diminishing it. But current mystery has its own value. It reminds us that nature still holds secrets, still surprises us. The invisible holding everything together is beautiful concept, poetic image, profound truth. We contemplate it as we drift toward rest, appreciating both what we know and what remains wonderfully unknown. As we approach the end of our exploration, let's reflect on living comfortably with dark matter's remaining uncertainties. Science often deals with uncertainty. Complete knowledge is rare. Mysteries persist even in well-understood fields. Dark matter exemplifies this beautifully. We know enough to be certain it exists. We don't know enough to identify it. This combination is scientifically healthy. Certainty without mystery is static. Mystery without certainty is chaos. Dark matter provides balance. Enough knowledge to constrain possibilities. Enough mystery to motivate exploration. Accepting this uncertainty requires intellectual humility. We acknowledge limits of current understanding. This is mature scientific stance, not weakness. Recognizing what we don't know is crucial for progress. Premature certainty, claiming to understand when we don't, hinders discovery. Dark matter keeps us honest. Despite decades of effort, its identity remains elusive. This should prevent overconfidence in our theories. Nature is more subtle than our imaginations. Uncertainty also makes science exciting. If everything were known, science would be merely educational, not exploratory. Dark matter ensures cosmology remains a dynamic field with major discoveries still possible. The next generation might solve dark matter puzzle, or it might remain mysterious longer. Either outcome is acceptable. Science progresses at its own pace. We cannot force discoveries. We can only continue systematic investigation, patiently accumulating evidence. Dark matter teaches patience. Decades of searching without definitive detection requires persistent patience. Researchers continue despite null results, refining experiments, exploring new parameter space. This dedication to long-term goals despite uncertain timeline embodies scientific spirit. Uncertainty also allows multiple approaches, without definitive answer. Various experiments and theories proliferate. This diversity is valuable. Different approaches might succeed where others fail. Having many research groups with different strategies increases overall probability of eventual success. Philosophically, uncertainty about dark matter connects to broader questions about knowledge and reality. Can we know things we cannot directly observe? Dark matter suggests yes, through systematic inference. But knowing something exists and knowing what it is are different. We achieve the first without yet achieving the second. This nuance, distinguishing different types of knowledge, enriches epistemology. Uncertainty about dark matter also affects how we communicate science to public. Honesty about what we don't know is important. Oversimplifying or claiming more certainty than warranted damages credibility. Explaining that dark matter exists but its nature is unknown conveys both confidence and humility. This balance helps public understand science as ongoing process, not fixed collection of facts. For scientists working on dark matter, uncertainty is daily companion. Experiments often produce null results. Observations don't always clarify as hoped. Maintaining motivation despite repeated non-detections requires psychological resilience. Yet researchers persist because the question matters. Understanding what holds universe together is worth pursuing. For students considering science careers, dark matter shows that unsolved problems exist at all levels. Fundamental questions remain unanswered. There's room for new discoveries and breakthrough insights. This should inspire rather than intimidate. Science needs new perspectives and fresh approaches. Embracing uncertainty means continuing inquiry while accepting that answers might not come quickly. It means valuing the process of investigation independent of immediate results. It means finding satisfaction in constraints and limits, not just in detections and discoveries. Science is journey, not just destination. The path of exploration has intrinsic value. Dark matter exemplifies this. Decades of research have taught us vast amounts despite not identifying the particle. We understand its role, distribution, properties, even without knowing what it is. This partial knowledge is significant achievement, even if incomplete. Embracing uncertainty also means being open to surprises. Dark matter might be completely unexpected. Perhaps it's not particles but something stranger. Perhaps multiple phenomena explain different observations. Perhaps our entire framework is slightly wrong, requiring conceptual revolution. Remaining open to these possibilities, not rigidly committed to preferred theories, is essential for science. Dark matter will eventually be understood. The question is when and by what means. Until then, we work with uncertainty, constraining possibilities, exploring mysteries, building knowledge piece by piece. This is science at its finest, systematic, patient, humble, persistent pursuit of understanding. As we conclude our journey through dark matter, let's synthesize understanding of this invisible foundation, holding everything together. Dark matter is scaffolding upon which visible universe is built. Without it, nothing we observe would exist. This makes it arguably most important component of cosmos despite its invisibility. Structure formation, galaxy evolution, cosmic web architecture all depend fundamentally on dark matter. It provides gravitational framework within which ordinary matter operates. Stars, planets, life itself are consequences of dark matter's gravitational influence. We exist because dark matter created conditions for complexity to emerge. This dependency is profound. The invisible supports the visible. The hidden enables the seen. Throughout our exploration, we've discovered dark matter through its effects. Rotation curves revealed it in galaxies. Lensing demonstrated it in clusters. CMB required it cosmologically. Convergent evidence from independent observations established its reality beyond reasonable doubt. We've explored what dark matter is not ordinary matter, not hot particles, not easily explained by modified gravity. We've considered what it might be: WIMPs, axions, sterile neutrinos, or something yet unconceived. We've discussed how it's searched for: direct detection, indirect detection, collider production, astronomical observation. We've examined its role, forming structure, holding galaxies together, shaping cosmic evolution. We've reflected on implications: philosophical, existential, practical, poetic. Dark matter reveals universe's hidden depths. Most of reality operates beyond direct perception. This should inspire both humility and confidence. Humility before nature's complexity. Confidence in science's power to reveal truth. The search for dark matter continues. Experiments improve, observations refine, theories develop. Eventually breakthrough will come. Dark matter's identity will be revealed. That discovery will rank among humanity's greatest intellectual achievements. Understanding what holds everything together will transform physics and cosmology. It might reveal an entirely new sector of nature with its own complex physics. Or it might be surprisingly simple, elegant solution hiding in plain sight. Either way, the discovery will be momentous. Until then, we live with mystery. We know dark matter exists without knowing what it is. This knowledge in ignorance is peculiar epistemic state but scientifically valuable. We understand enough to ask right questions and design appropriate experiments. We don't understand enough to rest satisfied. The search must continue. For you, tonight's listener, dark matter is now part of your cosmic understanding. You know that galaxies are held together by invisible matter, that most universe is hidden, that science reveals what we cannot see. This knowledge enriches your picture of reality. The cosmos is more mysterious and wonderful than it appears. Dark matter is invisible foundation supporting everything visible, the cosmic glue binding structures, the gravitational scaffold organizing matter. It's what holds everything together. Even though we cannot see it, touch it, or directly detect it. Through gravity's universal pull, dark matter shapes cosmic destiny and enables existence as we know it. We are, all of us, children of dark matter. Our existence traces back to its gravitational influence in early universe. It shaped the cosmic environment that eventually produced stars, planets, and life. Understanding this connection between invisible dark matter and visible life deepens appreciation for cosmic story. We're not separate from dark matter, but intimately connected to it through chains of causation, extending back to universe's first moments. Dark matter is a reminder that reality exceeds perception. Most important things are often invisible. Gravity itself is invisible. We observe its effects but never see the force. Time is invisible. We experience its passage but cannot directly perceive it. Dark matter joins these invisible fundamentals shaping existence. As we close this exploration, contemplate the invisible holding you, this planet, this galaxy, this universe together. Dark matter pervades everything, unnoticed but essential. Silent partner in cosmic dance. It asks nothing of us but provides everything. Gravitational stability enabling structure, time for complexity to develop. Framework for visible matter to organize. The universe's gift of the invisible. Dark matter's patient gravity assembled building blocks of existence over billions of years. Without fanfare, without visibility, without recognition, it performed essential cosmic service. This humility of dark matter, its complete self-effacement while doing crucial work, is profound metaphor. Most important work often goes unseen. Foundations support but remain hidden. Essential contributions lack visibility. Dark matter embodies this principle cosmically. As you rest tonight, know that invisible forces support you at every scale. Molecular bonds hold your body together. Electromagnetic forces structure atoms. Nuclear forces bind protons and neutrons. And beyond all this, dark matter's gravity holds the galaxy that holds the star that holds the planet that holds you. You're supported by cascading levels of mostly invisible forces and particles. Life exists within nested structures of hidden complexity. This should inspire awe. Reality is far richer than appearances suggest. What holds everything together is ultimately mystery in process of being revealed. Dark matter's identity awaits discovery. When found, new chapter opens in understanding cosmic architecture. Until then, we appreciate the mystery. We marvel at the invisible. We celebrate the search for understanding. Dark matter is what holds everything together. Galaxies, clusters, cosmic web, and ultimately the conditions permitting our existence. It is invisible foundation, hidden framework, silent scaffold supporting visible universe in all its glory. And through science's patient investigation, we've learned to see the unseeable through its effects, understand the incomprehensible through reason, know the unknowable through inference. This is triumph of human intellect meeting cosmic mystery. The search continues with wonder, patience, and hope. Thank you for journeying with me through the invisible universe, this patient exploration of dark matter and its role holding everything together. I hope you found peace in understanding that most of reality operates beyond sight, that the invisible supports the visible, and that science reveals what we cannot directly perceive. What holds everything together is dark matter, mysterious yet essential, unknown yet certain, invisible yet everywhere. Dark matter comprises 85% of universe's matter, creating gravitational scaffolding for all structure. Without it, galaxies wouldn't form, stars wouldn't ignite, planets wouldn't coalesce, life wouldn't emerge. We exist because dark matter shaped cosmic environment over billions of years. Its identity remains unknown despite decades of searching. Perhaps WIMPs, perhaps axions, perhaps something unexpected. The mystery persists even as evidence mounts. What we know, it exists, it's cold, it's collisionless, it dominates gravitationally. What remains unknown, its fundamental nature. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released the day's concerns. The mysteries we've explored perhaps help you feel both small in vast cosmos and significant in your capacity to understand invisible architecture supporting everything. Sleep well tonight, knowing you're embedded in dark matter halo, surrounded by invisible particles streaming through space and through you. They pass without interaction, yet their collective gravity holds the galaxy together. Dream peacefully of invisible scaffolds supporting visible structures, of gravitational frameworks organizing cosmic web, of hidden matter shaping everything we see. Dream of rotation curves revealing invisible mass, of gravitational lenses bending light around unseen matter, of computer simulations showing how dark matter assembled cosmic architecture. Dream of patient searches continuing in underground laboratories, of telescopes mapping dark matter's distribution, of scientists working to illuminate the dark. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward an appreciation for the invisible foundation supporting reality, wonder at cosmic mysteries, and understanding that what holds everything together operates mostly beyond sight. What holds everything together? Dark matter, invisible yet essential, unknown yet certain, hidden yet everywhere. the cosmic glue binding galaxies, the gravitational scaffold organising structure, the invisible foundation supporting visible universe. We are products of its influence, children of its gravity, seekers of its nature. Good night.